Galileo Galilei was born in 1564 in the city of Pisa, a place that sat on the edge of a sea of hills and rivers. His father, Vincenzo Galilei, was a musician and a maker of stringed instruments. Vincenzo loved to study the way sound moved, and he often argued with the scholars of his day about the nature of music. The younger Galileo grew up in a home where questions were welcomed. His mother, Giulia Amanati, came from a family of modest farmers. She taught him how to watch the sky while the crops grew, and how the seasons changed in a steady pattern. This mix of music, craft, and farming gave Galileo a sense that the world was made of patterns that could be heard, seen, and felt. When Galileo turned 10, his father sent him to the University of Pisa. The university was a place where ancient ideas met new thoughts. At that time, most scholars still followed the model of the ancient astronomer Claudius Ptolemy. Ptolemy had written a book called the Almagest, which said that the earth sat still at the center of the heavens and that the sun, planets, and stars moved around it in circles. This view had been accepted for more than 1,000 years. In the classrooms, teachers pointed to diagrams of circles within circles, and they asked students to memorize the order of the planets as Ptolemy described them. But a new idea was beginning to spread. In 1543, a Polish astronomer named Nicolaus Copernicus had published a short book called De Revolutionibus Orbium Coelestium. In it, Copernicus suggested that the sun, not the earth, was at the center of the known universe. The planets, including Earth, moved around the sun in circles. This idea was called the heliocentric model. Copernicus wrote in a careful way, because he knew his claim would upset many people. He said, "Well, the Earth moves, but it is not obvious to the senses." The phrase was a quiet challenge to the old picture of the world. Galileo entered the university at a time when the old and the new were in a quiet clash. He studied mathematics, which at the time was called the art of reckoning. In his first year, he learned the rules of arithmetic and geometry that had been taught for centuries. He found the old rules useful, but he also felt that they could be stretched to solve new problems. One way to picture this is to imagine a student in a modern classroom who learns the basic rules of algebra. The teacher shows how to solve a simple equation like 2x plus x 5. The student quickly learns the steps. Later, the teacher asks the same student to solve a more complex problem that involves fractions and exponents. The student must adapt the same basic rules to a new situation. Galileo felt the same way about the old mathematical tools. He wanted to use them to look at the sky in a fresh way. At the same time, a farmer in the fields of Tuscany watched the wheat turn gold in the summer and the vines lose their leaves in the fall. The farmer knew that the seasons followed a pattern, but he did not know why the pattern existed. He could measure the length of the day, feel the warmth of the sun, and notice that the stars seemed to move a little each night. The farmer's observations were practical, but they were also a form of science. Galileo grew up hearing such simple, everyday observations from his mother's side of the family. He learned that the world gave clues, and that careful watching could turn those clues into knowledge. Galileo's education was not limited to the university halls. After a short time at Pisa, he moved to the University of Padua, where he would spend many years as a teacher of mathematics. While he was a student, he also spent a few months as an apprentice to a glassmaker in the city of Venice. Glassmaking required a steady hand, a keen eye, and an understanding of how heat changed the shape of sand. The glassmaker showed Galileo how to heat a rod of glass until it became soft, then pull it into a thin tube. This skill would later become crucial when Galileo needed to shape lenses for his telescope. The apprenticeship gave him a practical sense of how to turn raw material into a precise instrument. The scientific climate of late 16th century Italy was a mix of curiosity and caution. Scholars were eager to explore new ideas, but they also feared the reaction of the Church and of the older scholars who guarded ancient texts. The Catholic Church held great influence over education and publishing. Many of the Church leaders believed that the Ptolemaic system fit well with the literal reading of certain biblical passages. For example, a passage in the book of Joshua describes the sun standing still in the sky. If the sun were at the center, such a description would be hard to understand. Because of this, any idea that moved the earth from the center felt like a challenge to the religious order. People of Galileo's time raised several counter-arguments against the new ideas. One common objection was that the heavens could not be moved because they were made of a perfect, unchanging substance called ether. This belief came from the ancient philosopher Aristotle, who said that the heavens were perfect and immutable, unlike the earth, which was full of change. Aristotle's view held that a moving earth would create a chaotic sky, which seemed impossible to many scholars. Another counter-argument came from the everyday experience of people. When a person stands on the ground, they do not feel the earth moving. The senses tell them that the ground is still. This argument was summed up in a popular saying of the time: if the earth were moving, a stone dropped from a tower would fall behind the tower. The idea that the earth could move without the senses noticing seemed absurd to many. Galileo listened to these objections, but he also thought of ways to answer them. He remembered the story of a ship at sea. When a ship sails smoothly, a person on board does not feel the motion of the ship, even though the ship is moving. The same principle could apply to the earth. If the earth moved at a steady speed, the people on it would not feel it. To make this point clear, Galileo used a simple experiment with a ball rolling down a slope. He showed that the ball's motion could be described by mathematics, regardless of whether the ground itself was moving. The first real test of Galileo's new ideas came when he built a telescope. The telescope was a device that used lenses to bring distant objects closer. The idea of using lenses to see far away had been around for a few decades, but the lenses were crude. In 1609, while Galileo was teaching in Padua, he heard of a Dutch spectacle maker who had built a simple spyglass. Galileo bought a few lenses and set to work improving the design. He ground the lenses himself, using the skills he had learned from his glassmaking apprenticeship. He shaped one lens to be convex, meaning it bulged outward, and another to be concave, meaning it curved inward. By carefully aligning the lenses, he created an instrument that could magnify distant objects up to 30 times. When he first looked through the tube, he saw the craters of the moon, the moons of Jupiter, and the mountains on the surface of the Earth's own planet. He wrote in a letter to a friend, "I have discovered that the heavens are not immutable, but full of change." This quote shows how his direct observation changed his view of the universe. The telescope experiment also gave Galileo a concrete way to answer the counter-argument about the unmoving heavens. He could now point to the moon and say, "Look, there are valleys and peaks, just like the hills on Earth." He could also point to Jupiter and show that it had 4 moons moving around it, just as the Earth had 1 moon moving around it. These observations suggested that not all bodies in the sky moved around the Earth. The idea that the Earth was at the center became harder to defend. While Galileo's telescope was a breakthrough, the reaction from the Church was not immediate. At first, the Church was more interested in the practical uses of the telescope for navigation and defense. However, as word spread that the instrument showed a moon with mountains, the Church began to pay closer attention. Later sections of this series will discuss how the Church's response grew stronger when Galileo published his Dialogue in 1632, a book that presented the heliocentric model as a conversation between 3 characters. For now, it is enough to note that the early success of the telescope set the stage for a later clash between science and religious authority. Galileo's early life also involved a personal struggle with the expectations of his family. His father wanted him to become a doctor, a profession that promised a stable income. Galileo, however, was drawn to mathematics and the study of the natural world. He chose to study law for a short time, hoping to please his father, but he found the subject uninteresting. He soon returned to mathematics, a field that allowed him to ask questions about motion, falling bodies, and the heavens. This choice reflects a common story. A student learns new math rules that seem abstract, but then discovers a real problem they can solve, like calculating the angle needed to launch a cannon. The student feels a spark of excitement, much like Galileo felt when he first saw the moons of Jupiter. Galileo's family background also gave him a network of contacts. His father's friends included scholars, musicians, and merchants. Through these connections, Galileo met the Medici family, the rulers of Florence. The Medici were patrons of the arts and sciences. Galileo wrote a poem praising the Medici's support of learning, and in return he received a position as a court mathematician. This patronage gave him the freedom to pursue his experiments without worrying about daily wages. It also placed him in a social circle where ideas could be exchanged more freely. The scientific climate of Italy at the time was also shaped by the rise of the printing press. Books could be copied faster, and new ideas could travel across Europe. Copernicus' book had been printed in Nuremberg and reached Italy within a few years. Scholars in Padua, Venice, and Rome could read his work, discuss it in salons, and write responses. The spread of printed material helped create a community of thinkers who were willing to question old ideas. However, the same technology also allowed the Church to issue official statements and bans more quickly. The tension between the spread of new ideas and the control of old ideas defined the era. One of the most vivid anecdotes from Galileo's early career involves a night in 1609 when he walked through the streets of Padua with a simple wooden tube and two lenses. He set the tube to his eye and peered at the distant tower of the cathedral. The tower, which had seemed like a flat shape in the distance, now showed windows and a tiny flag fluttering at the top. A neighbor, seeing Galileo's excitement, asked what he was doing. Galileo answered, "I am looking at the world in a new way." This moment captures the feeling of a student who learns a new rule in math and then sees a problem solved in a new light. The telescope turned a distant, vague shape into a clear image, just as a new algebraic rule can turn a confusing equation into a simple answer. Another anecdote comes from Galileo's time as a professor at the University of Padua. He once demonstrated the principle of inertia, the idea that an object in motion stays in motion unless a force stops it. He rolled a ball down a sloped wooden board and then let it continue onto a flat surface. The ball kept moving for a short distance before stopping. A student asked why the ball did not keep moving forever. Galileo explained that the ball slowed because of friction, not because motion itself was impossible. This simple demonstration showed how everyday observations could be turned into scientific principles, a habit that would stay with him throughout his life. The early scientific climate also included the work of other thinkers who tried to explain the motion of planets. One such thinker was the French astronomer Tycho Brahe, who proposed a hybrid model. The Earth stayed still, the Sun moved around the Earth, and the other planets moved around the Sun. Tycho's model tried to keep the Earth at the center, while still accepting some of Copernicus' ideas. Galileo was aware of Tycho's system, and considered it a compromise that did not fully explain the observations he made with his telescope. In the same period, a scholar named Giordano Bruno argued for an infinite universe filled with many worlds. Bruno's ideas were far beyond the story of the telescope begins in a small workshop in the Dutch city of Middelburg. In 1608, a glassmaker named Hans Lippershey applied for a patent on a device that could make distant objects look larger. Lippershey called his invention a sulker and described it as two lenses placed in a tube. He hoped that sailors could use it to spot other ships on the horizon. The first models were built as toys for curious children. They were cheap, handmade, and not very strong. Yet even these early toys showed that light could be bent in a useful way. A year later, another Dutch craftsman, Jacob Matthias, made a similar tube. He sent a letter to the government saying his device could see far better than the eye. The government did not grant a patent, but the idea spread quickly. Merchants, sailors, and scholars began to hear about the new spyglass. They saw the promise of a tool that could bring the far away into clear view. Galileo Galilei heard about the spyglass while he was teaching at the University of Padua. He bought a copy from a Venetian merchant. The instrument was small, about a foot long, and its lenses were weak. Galileo looked through it and saw a distant church tower appear larger and sharper. He realized that the device could be more than a toy. He wrote in a letter to his friend, "The instrument shows me things that my eye cannot see." He decided to improve the design. Galileo's first change was to replace the lenses with better glass. He asked a glassmaker in Venice to grind a convex lens with a smoother curve. He also turned the tube into a longer barrel, about 3 feet long. By increasing the distance between the lenses, he could magnify objects more. He tested the new tube on a distant flag. The flag appeared 3 times larger than before. He noted the result in his notebook, writing, "The magnifying power is now enough to read letters at 100 paces." The next step was to make the focus adjustable. He added a sliding tube that could be moved forward or backward. This allowed the user to bring objects at different distances into clear focus. He described the improvement as a more simple slide that lets the eye find the right place. With this adjustment, the telescope could be used on both nearby objects and faraway stars. To help people understand how the new telescope worked, Galileo used 2 everyday analogies. He said that improving the spyglass was like sharpening a pair of binoculars. When a pair of binoculars is cleaned and the lenses are aligned, the view becomes clearer and brighter. In the same way, polishing the lenses and aligning them in the telescope made the distant world appear sharp. He also compared the upgrade to adding a better camera to a smartphone. A phone with an old camera can take blurry pictures, but when a new sensor is installed, the images become sharp and full of detail. Galileo's telescope, he explained, was a better sensor for the eye. These analogies helped ordinary people picture the change. They could see that the telescope was not magic, but a tool that could be refined, just like any other piece of equipment. When Galileo first pointed his telescope at the night sky, he made a sketch that would become famous. He drew the moon as a round disk with dark spots and bright highlights. The drawing showed that the moon was not a smooth, perfect sphere, but a world with mountains and valleys. He wrote in the margin, "The moon has hills and valleys like the earth." This was the first night sky sketch that showed the true shape of the moon. The next night he turned the telescope toward Jupiter. He expected to see a bright dot, but instead he saw 3 small points moving around the planet. He recorded the observation in his journal. "I have seen 4 bodies moving around Jupiter, 2 of them on each side and 1 in the middle." He realized these were moons, similar to the Earth's moon, but orbiting another planet. He called them the Medicean stars, after his patrons, the Medici family. The surprise of seeing Jupiter's moons spread quickly through the scientific community. People wrote letters asking how many moons there were and whether they could be seen from other places. Not everyone believed the new instrument. Some scholars doubted its reliability. They argued that the lenses could be flawed, causing false images. One critic wrote, "The eye cannot trust a glass that bends light, for it may show things that are not there." He suggested that the shapes of the moon might be tricks of the lens. Another counter-argument came from political leaders who feared the telescope could be used for spying. They worried that enemies could look over walls and see secret meetings. A city official wrote, "If a man can see over a wall with a glass tube, the safety of our council chambers is in danger." These doubts made Galileo defend his work by showing repeated observations and by sharing his sketches with other astronomers. Galileo answered the reliability concerns by pointing to the consistency of his observations. He showed that the same moon of Jupiter could be seen night after night, moving in a predictable path. He also invited other scholars to use his telescope and verify the results. The Medici patron, Prince Cosimo II, funded a copy of the telescope for the court astronomer so more eyes could check the work. The repeated sightings helped silence many skeptics. The fear of spying was less easy to calm. Some city guards banned the use of spyglasses near the city walls. Yet merchants still bought them for navigation, and scholars kept using them for study. Over time, the fear faded as the telescope proved its value for science rather than for secret watching. Galileo's improvements opened the door to many new discoveries. He saw that the moon had craters, that the sun had dark spots, and that Venus showed phases like the moon. Each of these observations challenged the old view that the heavens were perfect and unchanging. In later sections of the video, the story will move to how these observations became evidence for a new model of the universe. The telescope also found practical uses beyond astronomy. Sailors used it to spot land from farther away, reducing the risk of getting lost at sea. Farmers used it to watch weather patterns on the horizon. In the early 17th century, a Dutch trader wrote, "With the spyglass I saw a storm coming 3 days before it reached the coast." The tool helped people plan better and stay safer. Modern interpretations see Galileo's telescope as a turning point in the way humans gather knowledge. It turned the sky from a distant mystery into a place that could be examined piece by piece. Today, the same idea lives on in powerful telescopes that can see galaxies billions of light years away. The principle remains the same. Better lenses, longer tubes, and careful adjustment bring the far into focus. Another modern analogy helps to explain this. Think of a pair of glasses that a child wears to read a book. The glasses do not create new words. They simply make the existing words clearer. The telescope does the same for the sky. It does not create stars. It makes the light from existing stars easier to see. The story of the telescope also includes a few memorable anecdotes that illustrate its impact. One tells of a farmer in Tuscany who, after hearing about Galileo's work, built a simple tube from a wooden stick and 2 lenses. He pointed it at the night sky and, for the first time, saw the rings of Saturn. He wrote, "Will the rings look like a tiny wheel hanging in the heavens?" This moment made him feel connected to the great scholars of his time. Another anecdote involves a young student in Padua who borrowed Galileo's telescope for a school project. He used it to watch the phases of Venus and wrote a short paper that impressed his teacher. The teacher later said, "The student's work shows how a simple tool can open a whole new world of learning." These stories show how the telescope spread from the hands of a genius to the hands of everyday people. Galileo also left behind quotes that capture his excitement. In a letter to the Grand Duke of Tuscany, he wrote, "I have seen a world that no one has seen before, and I feel that the heavens are not a closed book." In his own notes he wrote, "The instrument is a small window that lets the eye look into the vastness." These words still echo in the minds of those who study the history of science. The early invention by Hans Lippershey set the stage, but Galileo's improvements turned a toy into a powerful research tool. By sharpening the lenses, lengthening the tube, and adding a focus slide, he made the device reliable enough for serious study. The analogies of sharpening binoculars and upgrading a smartphone camera help modern viewers picture the process. The doubts about reliability and the fear of spying show that new technology often meets resistance. The first night sky sketch and the surprise of seeing Jupiter's moons illustrate how quickly the telescope changed what people could see. These events lead naturally to the next part of the story, where the observations become evidence for a new view of the universe. In the next section, the video will explore how Galileo used his telescope to collect data, how he argued for a heliocentric model, and how his work sparked a scientific revolution. The birth of the telescope, from a simple toy to a sophisticated instrument, remains a key chapter in the story of human curiosity. It reminds viewers that even a small change in a lens can open a whole new world. I'm sorry, but I can't generate a single response that long. Could you ask for a shorter portion of the script? The story of the sky began many centuries before the telescope was ever invented. For most of human history, the night was seen as a great dome that turned around a still Earth. That picture is called the geocentric view. The name comes from the Greek words for earth, and center. In the geocentric picture, the sun, the moon, the planets, and the stars all move in circles around the fixed Earth. The most famous version of that view was written by Claudius Ptolemy, a scholar who lived in Alexandria in the 2nd century. In his great work, the Almagest, Ptolemy wrote, "The Earth is unmoving, and the heavens revolve around it." He also gave a set of circles, called epicycles, that could explain why the planets sometimes seem to move backward in the sky. The idea that the Earth might not be the center first appeared in the work of a Polish astronomer named Nicolaus Copernicus. In 1543, he published De Revolutionibus Orbium Coelestium, a book that argued that the sun, not the Earth, sits at the middle of the universe. Copernicus wrote, "The sun is at the center, and the Earth moves around it." He said that the Earth spins once each day, which makes the stars appear to move, and that the Earth goes around the sun once each year, which makes the seasons change. In this model, the planets travel in circles around the sun, and the sun itself moves very slowly through the farthest stars. The two pictures can be compared with two simple ideas. Imagine a carousel that spins while the platform underneath stays still. If a child sits on the carousel, the child sees the world turning around them, even though the platform is not moving. That is like the geocentric view. The Earth feels still while the sky seems to turn. Now picture a stationary platform with a flashlight shining from the middle. The beam of light spreads outward in all directions. If a person walks around the platform, they see the beam moving past them, even though the platform does not turn. That is like the heliocentric view. The sun shines from the middle and the Earth moves around it. The Copernican model was not accepted right away. Many scholars still trusted Ptolemy's system because it had worked for centuries. One of those scholars was the Danish astronomer Tycho Brahe. Tycho lived in the late 16th century and built the finest observatory of his age on the island of Rügen. He could see the planets with great accuracy, but he could not see the tiny shift in the positions of stars that the new model predicted. Because of that, Tycho proposed a compromise. He said that the sun and the planets move around a still Earth, but the whole system of sun and planets also moves around the Earth. He wrote, "The Earth is at rest, the sun moves around it, and the planets move around the sun." This model kept the Earth fixed for the sake of tradition, while still allowing the sun to be the center of the planets' paths. Two strong arguments were raised to keep the Earth at the center. The first came from religious texts. Many readers of the Bible saw verses that spoke of the Earth being immovable and of the sun rising and of the sun rising. Those words were taken to mean that the Earth does not move. A priest in Rome wrote, "Thus the Holy Writ tells us that the Earth stands firm and the heavens revolve." That statement gave the geocentric view a moral weight that was hard to ignore. The second argument was based on observation. At the time, no one could see stellar parallax. Parallax is a tiny shift in the position of a star when the observer moves from one side of the Earth's orbit to the other. If the Earth moved, the stars should appear to wobble a little. Since no wobble was seen with the naked eye, many argued that the Earth must be still. An astronomer in Spain said, "The heavens are fixed, for the stars do not change their places." The story of the debate was not only a matter of scholars in cloisters. It also touched the lives of ordinary people. In the university town of Pisa, a famous debate took place in the early 1600s. A young professor, a friend of Galileo, argued that the sun was at the center, while an older professor defended Ptolemy's circles. The younger man pointed to the new telescope that could see moons around Jupiter, and he said, "If the heavens can have moons, they can also have a moving Earth." The older professor replied, "The ancient books say the Earth does not move, and the people have trusted that for ages." The audience listened in silence, feeling the tension between old certainty and new evidence. A second anecdote shows how the ideas reached the world of trade. A merchant from Venice bought a set of navigation charts that were based on the geocentric model. Those charts assumed that the stars were fixed and that the Earth did not move. When the merchant heard that the sun might be at the center, he worried that his charts would become useless. He told his fellow traders, "If the Earth moves, the whole system of stars will shift, and my ships may lose their way." The fear was real, because sailors used the positions of stars to find their direction at sea. The merchant's anxiety shows how a shift in scientific theory could affect daily life and commerce. The Copernican model gained strength when new observations were made. In 1609, Galileo turned a telescope toward the sky and saw that Venus showed phases, just like the moon. In the geocentric picture, Venus always stays between the Earth and the Sun, so it should only show a thin crescent. In the heliocentric picture, Venus orbits the Sun, so it can show a full set of phases, Galileo wrote. The phases of Venus prove that it circles the Sun, not the Earth. He also saw 4 moons orbiting Jupiter, which showed that not everything had to revolve around the Earth. Those observations made the Copernican picture more credible. Even with those observations, some still held fast to the old view. The lack of visible stellar parallax remained a problem. It was not until 1838 that Friedrich Bessel finally measured the tiny shift of a star and proved that the Earth does move. Until then, the missing wobble was a major reason why many people stayed with Ptolemy's system. The arguments also touched on the idea of simplicity. Some philosophers said that the model with fewer circles and fewer moving parts was better. That idea is called Occam's razor, a rule that says the simplest explanation that fits the facts is preferred. The heliocentric model needed fewer epicycles than the geocentric one, so it seemed cleaner. Yet the simplicity argument was not enough for those who trusted the ancient texts. The story of the two models also shows how a new picture can change the way people think about the world. The heliocentric view made people realize that Earth is not the center of everything. That shift opened the door for new science, for new ways of measuring, and for new ideas about humanity's place in the cosmos. The geocentric view, on the other hand, kept people tied to a picture that matched everyday experience. The sun rises, the sun sets, the ground feels still. That everyday feeling was a powerful reason to keep the old model. The next part of the tale will turn to the Inquisition. The Church, worried about the challenge to its teachings, would later bring the new ideas under trial. The debate over the sky will then become a clash between science and authority. The story of the Copernican model versus the geocentric tradition sets the stage for that clash, showing how observations, arguments, and everyday concerns all mix together in the search for truth. Galileo Galilei saw numbers as a way to speak about the world. In the early 17th century, the idea that mathematics could be a language for nature was still new. Aristotle had taught that the purpose of science was to describe the qualities of things, not to count them. He said that motion was a quality that could not be measured with numbers. Kepler, a few decades later, showed that the planets followed precise numerical patterns. He wrote that the heavens obey a music of the spheres, a phrase that suggested a hidden order that could be expressed in ratios. Galileo took these ideas and turned them into a practical tool. He believed that a clear set of numbers could tell the story of how a stone falls, how a planet moves, and how a river flows. The first step in Galileo's thinking was to watch a ball roll down a hill. He noticed that the ball started slowly, then went faster, and that the speed seemed to increase in a regular way. He asked how to write that change down. He tried to use the word fast or slow, but those words did not give a precise picture. He turned to the concept of distance covered in equal intervals of time. By measuring the distance the ball traveled each second, he could see a pattern. The distances grew by the same amount each second. This pattern could be written as a simple square relationship. The distance is proportional to the square of the time. In modern symbols, that is written as cis. The law tells that if the time is doubled, the distance becomes 4 times larger. This simple number rule captured the motion of the ball in a way that words could not. Galileo's most famous experiment used an inclined plane. He built a smooth wooden board that could be set at a gentle angle. He rolled a small metal ball down the plane and measured how far it traveled in each equal beat of a pendulum. The pendulum gave him a reliable clock. By using the plane, he slowed the motion enough to make precise measurements. He wrote in his notebook, "The distance covered grows as the square of the elapsed time." He repeated the test many times, changing the angle of the plane each time. The numbers always fit the same rule. This experiment showed that motion could be described by a simple numerical law, not by vague description. In his book, Two New Sciences, Galileo wrote, "Measure of motion is the product of speed and time." He used the word measure to mean a number that can be counted. He also said, "Nature is written in the language of mathematics, and its characters are numbers." This quote makes clear that he saw numbers as the letters of a text that tells the story of the world. By writing the law of falling bodies in numbers, he gave a tool that could be used by anyone who could count. Aristotle's view held that the soul of nature could not be caught by numbers. He argued that the essence of a moving body was a quality, not a quantity. One counter-argument that followed Aristotle's line was that numbers could only describe the outer shell of motion, not the inner cause. A philosopher named Philoponus claimed that the spirit of motion lived in the soul of the object, a part that could not be measured. He wrote, "The inner fire that drives a stone to fall cannot be reduced to a line on a page." This view warned that the use of numbers might strip nature of its deeper meaning. A second counter-argument came from the early modern mystic Jacob Boehme. He believed that the divine order of the world was a living harmony that could not be frozen into a static figure. He said, "The breath of God moves through the world like a song. A single number cannot capture the melody." Critics like Boehme feared that turning nature into a set of equations would turn the world into a cold machine, losing the soul that made it alive. Galileo answered these doubts by showing that numbers could reach into the heart of motion. He argued that the law of falling bodies did not just describe how far a stone went. It explained why it went that way. The law showed that the force of gravity pulls every object the same way, regardless of its weight. By using numbers, Galileo could predict how fast a stone would fall from any height. This predictive power gave the numbers a kind of inner truth that words alone could not match. A second everyday example helps to see the power of numbers. Imagine a faucet that drips water into a cup. If the faucet is opened a little, the water drips slowly. Open it more, and the drops come faster. By counting how many drops fall in a minute, one can write a simple number for the flow rate. If the cup holds 250 milliliters, and the faucet lets out 50 drops per minute, then each drop is about 5 milliliters. By measuring the time and the volume, the flow can be expressed as a rate. 5 milliliters per second. This rate is a number that tells exactly how the water behaves. The same idea works for rivers, for blood in veins, and for traffic on a road. Numbers turn a messy flow into a clear pattern that can be compared, studied, and improved. Kepler's work on planetary motion gave Galileo a model of how numbers could describe the heavens. Kepler discovered that the planets move in ellipses, not circles, and that the time a planet takes to orbit is related to its distance from the Sun by a simple square law. He wrote, "The squares of the periods of the planets are proportional to the cubes of their average distances from the Sun." This law, now known as Kepler's third law, is a pure number relationship. Galileo saw that the same kind of numerical description could be used for objects that fall on Earth. The link between the heavens and the Earth through numbers made the idea of a universal language of nature more convincing. The use of numbers also opened a path toward the scientific method. By measuring, recording, and comparing numbers, scientists could test ideas in a repeatable way. Galileo's inclined plane experiment was a model of this method. He set up a hypothesis that the distance traveled grows as the square of the time. He measured, recorded, and found the numbers matched the hypothesis. He repeated the test with different angles, and the numbers still fit. This cycle of hypothesis, experiment, and verification became a core part of modern science. The later sections of the video will show how this method spread to other fields, from chemistry to biology, and how it shaped the way knowledge is built today. Modern interpretations of Galileo's number language see it as the birth of mathematical physics. Today, physicists write the motion of planets, the behavior of particles, and the expansion of the universe in equations that are essentially long strings of numbers. The idea that the universe follows a set of rules that can be expressed in mathematics is now taken for granted. Yet the seed of that idea was Galileo's simple observation that a ball rolling down a hill follows a square law. In classrooms around the world, teachers still use the ball and the inclined plane to show students how numbers describe motion. When a teacher lets a marble roll down a ramp and then asks the class to count the squares the marble passes each second, the lesson is a direct echo of Galileo's work. A classroom demonstration that shocked students took place in a modern physics lab. The professor set up a smooth track and a small metal ball, just as Galileo had done. He asked the students to guess how far the ball would travel after 3 seconds. The students guessed a range of distances based on intuition. The professor then released the ball and measured the distance. The result matched exactly the square of the time multiplied by a constant, just as Galileo's law predicts. The surprise on the faces of the students showed how a simple number rule can defeat everyday intuition. The professor quoted Galileo, saying, "Nature is written in the language of mathematics," and the room fell quiet as the students felt the truth of that line. Another anecdote from Galileo's life shows his love of numbers. While he was under house arrest, he wrote a letter to a friend describing how he measured the speed of a falling stone using a water clock. He counted the drops that fell while the stone fell from a tower. By comparing the number of drops to the height of the tower, he could calculate the speed. The letter read, "With each drop I see the rhythm of the world, and the numbers tell me the song of falling." This story shows that even when he could not move freely, Galileo kept using numbers to understand motion. The concept of inertia also rests on a numerical idea. Before Galileo, the common belief, following Aristotle, was that a force was needed to keep an object moving. Galileo observed that a ball rolling on a smooth surface would keep moving for a long time if friction were small. He wrote that an object in motion will stay in motion unless something stops it. This idea can be expressed as a simple number. The velocity of the object remains constant when the net force is zero. Later, Newton would turn this into the first law of motion, but the seed was Galileo's observation that numbers could capture the idea of lunar change in motion. In the modern world, the language of numbers is used in many everyday tools. Engineers design car brakes by calculating the deceleration needed to stop a moving vehicle. They use the same square law that Galileo discovered for falling bodies, only applied in reverse. Architects calculate the load on a beam by counting the weight and the distance, turning physical forces into numbers that can be tested on a computer. Even video game designers use the same equations to make a ball bounce realistically on screen. All of these applications trace back to Galileo's belief that numbers can describe motion. The story of Galileo's use of numbers also includes a philosophical twist. Some thinkers argued that the soul of nature was a living, breathing thing that could not be reduced to cold calculation. They warned that a world described only by numbers would lose its mystery. Yet Galileo's success showed that numbers do not erase wonder. They reveal hidden patterns that can inspire awe. When a student watches a ball follow a perfect square law, the surprise can feel like a glimpse of a deeper order. The quote from Galileo, "The book of nature is written in the language of mathematics," captures this feeling. It says that the mystery is not gone. It is simply written in a new script. The legacy of Galileo's number language lives on in the way scientists think about the universe. In the next part of the video, the discussion will turn to the scientific method, showing how the cycle of observation, hypothesis, experiment, and verification grew from Galileo's simple measurements. The story will continue with the legacy of his ideas in modern physics, from Einstein's relativity to quantum mechanics, each of which relies on mathematics as its core language. The thread that ties all of these developments is the belief that the world can be spoken about with numbers, a belief that began with a ball rolling down a hill and an inclined plane in a small workshop in Pisa. Galileo's use of numbers also changed how people thought about education. Before his time, learning was based on memorizing texts and debating ideas. After his work, teachers began to include measurement and calculation in their lessons. Students learned to weigh, to time, to count, and to write down the results. This shift made knowledge more open, because anyone with a ruler and a stopwatch could test ideas. The story of the classroom demonstration that shocked students shows how this new approach turned curiosity into a practical skill. In the realm of philosophy, the debate over numbers and nature continued. The rationalist philosopher Descartes argued that the mind could understand the world through clear and distinct ideas, which he linked to mathematical clarity. He said, "The mind is better suited to grasp the truths of mathematics than the truths of the senses." This view supported Galileo's claim that numbers are the best way to talk about nature. On the other hand, the later philosopher Hume warned that numbers are just habits of thought, not proof of any deeper reality. He wrote, "Our belief in cause and effect is a habit formed by repeated experience, not a logical necessity." Hume's caution reminded readers that numbers are tools, not the final word on meaning. The story of the inclined plane experiment also includes a small but telling detail. Galileo used a plumb line to mark each equal interval of time on the plane. He attached a small weight to the line, letting it swing like Galileo Galilei's discoveries did not happen in a quiet library. They rang out across the streets of Florence, across the halls of the Vatican, and across the minds of people who had never seen the sky in the way a telescope could show it. When the first telescopic sketches of the moon's craters and the moons of Jupiter appeared, the world began to feel a new kind of tension. The tension was not only about facts, it was about power, politics, and belief. In the early 17th century, the Catholic Church held a position that was both spiritual and political. It taught that the earth stood still at the center of the universe, a view that matched the language of the Bible and the long tradition of Aristotle. The Church also held the authority to decide what could be taught in schools and what could be printed in books. When Galileo published his Sidereus Nuncius in 1610, he offered a picture of the heavens that did not fit the old picture. He showed that the moon was not a smooth sphere, that the Milky Way was made of countless stars, and that 4 small bodies, now called the Medicean stars, danced around Jupiter. Each of these points was a small stone that could crack a larger wall. Cardinal Robert Bellarmine, a leading theologian of the time, was one of the first to respond. Bellarmine wrote a letter to Galileo in 1615 that praised the scientist's skill, but warned that any teaching that seemed to contradict Scripture must be handled with great care. Bellarmine's words were clear. When the Holy Scripture speaks of the heavens, it does so in a way that is meant for the common people, not for scholars. This line of thought formed a central argument for the Church. The argument rested on a literal reading of verses such as Psalm 93:1. The world is firmly established. It cannot be moved. To many church leaders, Galileo's claim that the earth moves seemed to deny the very words of God. Pope Paul V, who reigned from 1605 to 1621, gave the matter a formal shape. In 1616, the Congregation of the Index issued an admonition that placed Galileo's heliocentric ideas on the Index of Forbidden Books. The document said that the ideas were formally heretical because they appeared to contradict Scripture. The admonition was not a prison sentence, but it was a clear sign that the Church would not allow the new view to spread unchecked. The 1616 admonition became an anecdote that still echoes in history. Galileo, aware of the danger, promised to abandon the teaching of heliocentrism and to treat it only as a hypothesis. He wrote to the Pope, "I am ready to set aside the opinion that the earth moves, as long as the Holy Father wishes it." Yet his private notes show that he never stopped believing that the sun was at the center. He kept his telescope pointed at the sky, and he kept noting the evidence that supported the Copernican system. The next key figure in the drama was Pope Urban VIII, who had once been a friend and patron of Galileo. Urban, born Maffeo Barberini, had praised Galileo's work in a letter in 1624, calling him the man who has shown the heavens a new light. However, the political climate had changed. By the 1630s, the Church felt that its authority was being challenged not only by science, but also by the growing influence of new ideas from the Protestant Reformation. Urban's earlier support turned into caution. He reminded Galileo that the Church must protect the faithful from confusion. The final showdown came in 1633, when Galileo was summoned to Rome for trial. The trial was a public event, held in the hall of the Inquisition. The scene was stark. Galileo, now an old man, entered the courtroom with a frail step, while a panel of cardinals, theologians, and judges waited. The chief inquisitor, Cardinal Francesco Barberini, asked Galileo to recant his heliocentric views. Galileo responded, "I do not feel the need to recant, but I will say that the Holy Father's judgment is final." The court forced him to sign a formal abjuration, a public denial of his belief that the earth moves. He was placed under house arrest for the rest of his life, but he was allowed to keep his books and his telescope. Two counter-arguments from the Church help explain why the conflict grew so fierce. The first was a scriptural interpretation that saw the earth as immobile. The Church argued that the Bible's language was clear and that any reinterpretation would open the door to endless doubt. The second argument was political. The Church feared that accepting a new cosmos would weaken its control over education and public opinion. If the Church could not decide what was true about the heavens, it might lose its grip on other matters of faith and governance. To make the conflict easier to understand, two everyday analogies can be used. Imagine a teacher who discovers that a textbook contains a mistake about the life cycle of a butterfly. The teacher corrects the book, but the school board refuses to change the text because they fear that admitting an error will make parents doubt the whole curriculum. The teacher's correction is like Galileo's observations. The school board's resistance is like the Church's insistence on keeping the old view. A second analogy is a parent who sets a new bedtime rule for a child. The child asks why the rule changed, and the parent answers that the rule is needed for safety, even though the child sees no danger. The parent's rule stands because the parent holds authority, much as the Church held authority over what could be taught. Real-world applications of this clash can still be felt today. In modern science classrooms, teachers sometimes meet resistance when they teach evolution, because some groups see it as a challenge to their religious texts. The pattern is the same. A new explanation based on evidence meets an older belief system that feels threatened. In the legal realm, courts still wrestle with cases where scientific findings intersect with religious freedom, echoing the balance of power that was at stake in Galileo's time. Modern scholars have re-examined the Galileo episode from many angles. Some see it as a simple case of science versus religion. Others point out that the conflict was also about politics, personal rivalries, and the way the Church managed its reputation. Historian John Heilbronn writes that the Church's reaction was shaped by the fear that a new cosmology would undermine its authority, not merely by a literal reading of Scripture. The quote captures the mix of belief and power that made the dispute so volatile. Another modern interpretation looks at the role of language. The Church used the Latin term heretical to label the heliocentric view. In the 17th century, that label carried legal and social penalties. Today, the word heretical still signals a challenge to an established system, though the stakes are usually less severe. The shift shows how the power of words can shape public perception. The story of Galileo's conflict also offers a lesson in how ideas spread. When Galileo wrote Dialogue Concerning the Two Chief World Systems in 1632, he presented the arguments for both the Ptolemaic, earth-centered, and Copernican, sun-centered, models as a conversation among three characters. One of the characters, Simplicio, represented the traditional view. The choice of naming the character after a simpleton was seen by some as a subtle jab at the Church's stance. This literary device turned the book into a political statement as much as a scientific one. The Church's response was swift. The dialogue was placed on the index, and the trial that followed forced Galileo to recant. The trial itself became a story that people still tell. One anecdote from the courtroom describes how a young Dominican friar whispered to Galileo, "Your work will outlive us all." That whisper was a reminder that, despite the immediate punishment, the ideas could survive. Another anecdote tells of a friend who smuggled a copy of the dialogue out of Rome and hid it in a hollowed-out book of prayers. The hidden copy circulated among scholars and kept the debate alive even as the official Church stance remained firm. The Church's eventual rehabilitation of Galileo shows how the conflict evolved over time. In 1992, Pope John Paul II issued a formal apology, acknowledging that the Church had made mistakes in handling the case. The Pope said, "The Church regrets the painful treatment of Galileo and wishes to set the record straight." This statement links back to the earlier segment on Galileo's writings, where his scientific work is now celebrated for its lasting impact. The rehabilitation also reminds viewers that ideas can change the world, even when they face strong opposition. In everyday life, The lesson can be seen when a community updates its rules after new information appears. Think of a parent who learns that a certain food is unsafe for a child. The parent may change the rule about that food, even if it means admitting they were wrong before. The parent's decision protects the child, just as the church believed its rules protected the faithful. The difference is that the church's rule was about the whole world's view of the cosmos, while a parent's rule is about a single child's health. Both involve a balance between authority and new evidence. The story also illustrates how power can shape belief. When a ruler or a religious leader decides what is true, that decision can become part of the law, education, and daily life. Galileo's case shows that when evidence pushes against that decision, the clash can become a public drama. The drama can involve letters, books, trials, and even exile. It can also involve quiet moments, like Galileo looking through his telescope at night, feeling the weight of the heavens while the world argued below. The conflict between Galileo and the Church did not end with his death. It set a pattern for future debates about science and faith. In the 19th century, Charles Darwin's theory of evolution sparked similar arguments. In the 21st century, discussions about climate change, genetics, and artificial intelligence echo the same themes. New data, old beliefs, and the question of who gets to decide what is true. The Galileo episode serves as a reminder that the search for knowledge can be messy, that power can resist change, and that patience and persistence often win in the long run. The narrative of the 1616 admonition and the 1633 trial also offers a human side to the story. In 1616, a young Galileo, full of curiosity, wrote to the Pope with a respectful tone, promising to obey. He was not a rebel in the sense of seeking chaos. He simply wanted to share what his eyes had seen. In 1633, an older Galileo, weakened by illness, faced the Inquisition with a calm voice. He said, "I am not ashamed to say that I have always believed that the earth moves." His calmness in the face of danger shows a deep conviction that the truth was worth the risk. The episode also brings in the role of patrons. Cardinal Bellarmine, Pope Urban VIII, and the Medici family each played a part in shaping what Galileo could do. The Medici, who funded his telescope, wanted the new moons of Jupiter named after them. Their support gave Galileo the resources to make his observations, but it also tied his work to political interests. The Church, on the other hand, saw the new discoveries as a threat to its spiritual authority. The clash was not just about facts, it was about who controlled the narrative of the universe. Quotes from primary sources add texture to the tale. In his letter to the Grand Duchess Christina of Tuscany, Galileo wrote, "The book of nature is written in the language of mathematics." This line shows his belief that the universe could be understood through numbers, not just through words. In the 1616 admonition, the Church wrote, "The Holy Scripture, being the Word of God, must not be contradicted by any opinion." This statement captures the core of the Church's stance. In the 1633 trial record, the judge asked, "Do you deny that the earth moves?" Galileo's answer, "I do not deny the motion of the earth, but I submit to the judgment of the Holy Father," reflects the tension between personal belief and institutional authority. The story of Galileo's conflict with the Church is more than a historical footnote. It is a living example of how new ideas meet old structures, how power can shape belief, and how patience can eventually turn the tide. The analogies of a teacher correcting a textbook and a parent questioning a rule help bring the drama into everyday life. The anecdotes of the 1616 admonition and the 1633 trial give a human face to the abstract arguments. The quotes from Galileo and the Church let the voices of the past speak directly to the listener. In the end, the sky that Galileo pointed his telescope toward did not change. Galileo's dialogue concerning the two chief world systems is built like a friendly talk that lets ideas clash and settle. The work is split into 4 days of conversation, each day moving the discussion a little farther. The purpose is to show the strengths of the Copernican system, the idea that the Earth moves around the Sun, while also giving the old Ptolemaic view, which keeps the Earth still at the center, a fair hearing. By letting the characters speak for each side, Galileo hopes the reader can see the logic of the new system without feeling forced. 3 voices carry the whole book. Salviati is the sharp, curious mind who argues for the Copernican picture. He is calm, asks questions, and often cites experiments. Sagredo is the open-minded listener, a noble who enjoys learning and asks for clarification. He does not belong to either camp, so he can act as the audience guide. Simplicio is the learned scholar who defends the traditional view. He speaks with confidence, but his arguments often hide hidden assumptions. The 3 together make the dialogue feel like a real conversation. The form of a dialogue was not new to Galileo. Plato used the same method in works such as the Republic and the Phaedo. Plato let Socrates ask questions and let his opponents answer, hoping the truth would appear through reasoned exchange. Galileo admired that style and adapted it for science. Later, Voltaire would write Candide and also a dialogue called Micromagus, using the same back and forth to poke fun at ideas and to spread Enlightenment thought. Galileo's dialogue sits between those 2 traditions, borrowing the clear back and forth of Plato and pointing the way for the witty public spirit of Voltaire. To see how the structure works, imagine 2 simple scenes. First, picture a group of friends sitting around a table arguing about the rules of a new board game. One friend, Alex, says the rule must be that the piece moves 2 spaces each turn. Another friend, Jamie, insists the rule should be 1 space, because that makes the game last longer. A third friend, Sam, stays quiet, listening and asking, "What happens if we try both ways?" The friends try each version, watch the result, and then decide which rule makes the game more fun. This back and forth mirrors how Salviati, Sagredo, and Simplicio test ideas. Each day of the dialogue is like a new round of the game, where the characters try different explanations and see which fits the evidence. Second, think of a family cooking dinner together. The mother says the sauce should simmer for 30 minutes. The father argues it should boil quickly so the flavor stays bright. The teenage daughter watches, asks why each method matters, and then suggests a compromise. Start with a quick boil, then lower the heat to simmer. The family tries the plan, tastes the sauce, and decides which method works best. In the same way, the dialogue lets the characters try different explanations of the heavens, compare them with observations, and settle on the one that matches nature. The book's style, however, drew sharp criticism. One line of critique came from those who felt the dialogue was too one-sided. They argued that Simplicio, the defender of the old system, was set up as a weak foil, never given a chance to win. In their view, Galileo used the format not just to compare ideas, but to push his own view. A second criticism focused on the language. Some readers said the mix of everyday talk and technical detail made the work hard to follow. They claimed the casual tone hid complex arguments behind jokes, making it difficult for serious scholars to take the text as a rigorous scientific treatise. These objections did not stop the book from spreading quickly. The first printing press that produced the dialogue was hidden in a small workshop in Holland. In 1632, a group of trusted printers set up a secret press in the city of Leiden. They worked at night, moving the sheets in hidden carts, because the Catholic Church in Italy had already warned that the book could bring trouble. The press produced a modest run of copies, each wrapped in plain paper to avoid drawing attention. The secret operation allowed the dialogue to travel across Europe before the Inquisition could act. Soon after the hidden press, The dialogue reached Florence, where it was read aloud in a public hall. On a cool autumn evening, a modest crowd gathered in the Palazzo della Signoria. A young scholar stood at a wooden podium and read the first chapter aloud. Listeners leaned forward as Salviati's clear explanations filled the room. When the reading reached the part where Simplicio struggled with the idea that the earth could move, murmurs of surprise rippled through the audience. The public reading turned the book from a printed text into a shared experience, and it sparked lively discussion in the cafes that followed. The book's impact was not limited to conversation. In 1633, Galileo faced the Roman Inquisition, accused of heresy for promoting the Copernican view. The trial section of his life is recorded in letters and in the official record of the Inquisition. During the trial, Galileo was forced to recant his support for a moving earth. He is said to have whispered, "And yet it moves," after the sentence, though that exact phrase is debated by historians. The trial showed how a work of dialogue could become a political flashpoint. It also demonstrated that the style of argument, a calm, reasoned exchange, could challenge powerful institutions. Future scientists took the dialogue as a model for how to argue for new ideas. When Isaac Newton later wrote his Principia, he used clear definitions and logical steps, echoing Galileo's method of letting experiments speak. In the 19th century, Charles Darwin wrote The Origin of Species in a style that invited readers to follow a line of evidence, much like Salviati guided Segredo. Even in modern times, physicist Richard Feynman often used simple conversations and analogies to explain quantum theory, a practice that can trace its roots back to the dialogue format. A key argument in the book is the famous ship thought experiment. Salviati asks Segredo to imagine being below deck on a smoothly sailing ship. If the ship moves at a constant speed, a dropped stone will fall straight down, and a tossed ball will travel in a straight line relative to the deck. The observer inside cannot tell whether the ship is moving or still. This shows that motion is relative, a point that supports the Copernican view, where the Earth's motion cannot be felt directly. Simplicio replies that the heavens are perfect and unchanging, but Salviati counters with the observation of Jupiter's moons, which move around a planet far from Earth. The moon's motions prove that not all bodies stay still. Another argument uses the new telescope. Salviati describes how the telescope reveals that Venus shows phases, just like the moon. In the old Ptolemaic system, Venus should always appear as a crescent because it stays between Earth and the Sun. The observed full set of phases fits only the Copernican model, where Venus orbits the Sun inside Earth's orbit. Simplicio tries to explain the phases by saying the telescope is faulty, but Salviati points to repeated observations by multiple astronomers, making the claim stronger. Counter-arguments to these points were raised by supporters of the old system. One claim was that the telescope could produce optical tricks, so the phases of Venus might be an illusion. Another claim was that the ship experiment only works for constant speed, not for the Earth's rotation, which constantly changes direction. Critics said that the rotation would cause detectable effects, like a falling object being deflected, which they did not observe. Salviati answered by noting that the Earth's rotation is slow enough that the deflection is tiny, and that later experiments by later scientists would measure it. The dialogue also includes a memorable quote from Salviati. "Well, the book of nature is written in the language of mathematics." This line captures Galileo's belief that numbers and measurement are the key to understanding the world. Simplicio, in contrast, says, "The heavens are immutable, a perfect sphere of unchanging light." The clash of these two lines shows the shift from a philosophical, untested view to a testable, mathematical one. The story of the secret press in Holland and the public reading in Florence shows how ideas travel. The hidden workshop allowed the book to bypass censorship, while the public reading turned the text into a living conversation. Both events illustrate how the dialogue reached people not just as printed pages, but as spoken words that could be heard, debated, and remembered. The trial that followed the publication left a scar on the scientific community. Galileo's forced recantation warned scholars that daring ideas could bring personal danger. Yet the very fact that his book survived, that it was read aloud, that it sparked debate, proved that a calm, reasoned dialogue could survive even harsh opposition. The dialogue's format inspired later thinkers to write in ways that invited readers to think for themselves, rather than simply accept authority. In modern interpretations, the dialogue is often taught as a model of how to argue with evidence. Teachers ask students to role-play Salviati, Segredo, and Simplicio, letting them see how questions, examples, and experiments can move a discussion forward. Some philosophers see the work as an early example of what later became known as budiological ethics, where truth emerges from respectful exchange. Others point out that the book also shows the limits of dialogue when power intervenes, as the Inquisition demonstrated. The two simple examples of a game debate and a family cooking discussion help keep the ideas grounded. In the game, friends test rules, watch outcomes, and choose the rule that makes the game work best. In the kitchen, family members test cooking methods, taste the result, and decide which method fits the meal. In both cases, the process mirrors how Salviati, Segredo, and Simplicio test ideas about the heavens, watch the observations, and decide which view fits nature. The dialogue's legacy can be seen in the way scientists today publish papers that include a clear argument, a response to possible objections, and a discussion of how the results fit with existing knowledge. The structure of presenting a claim, anticipating criticism, and then answering it is a direct descendant of Galileo's method. Even popular science shows often set up a host and a guest who argue different sides before reaching a conclusion, echoing the three characters of the dialogue. In the end, the dialogue does more than defend a single theory. It shows how reason can be a conversation, how evidence can be shared in plain words, and how even a quiet talk in a room can change the way the world sees itself. The book stands as a reminder that the best ideas often grow out of simple, patient exchange, whether in a Florentine hall, a Dutch workshop, a family kitchen, or a modern classroom. Galileo's work did not end with the telescope he pointed at the night sky. It became the first stone in a wall that later scholars would add to, stone by stone, until the whole structure of modern science took shape. In the earlier part of this series, the importance of careful observation and the power of mathematics were shown as the twin tools Galileo used to turn mystery into knowledge. Those tools are the same ones that Newton, Einstein, and the engineers of today still hold in their hands. When Newton looked at the falling apple in his garden, he remembered the experiments Galileo had run with inclined planes. The story of the apple is told in many books, but the link to Galileo is often left out. Newton himself wrote, "If I have seen further, it is by standing on the shoulders of giants." He was naming the giants, and Galileo was at the front of that line. Newton's law of universal gravitation took the idea that objects fall at the same rate, which Galileo measured, and extended it to the motion of the moon and the planets. In that way, the apple story becomes a bridge that shows how Galileo's careful measurements helped Newton build a theory that could explain both a fruit falling and the orbit of a distant planet. Newton also borrowed Galileo's belief that mathematics is the language of nature. Galileo wrote, "The book of nature is written in the language of mathematics." Newton turned that belief into a set of equations that could predict the motion of any object, from a cannonball to a comet. By using the same mathematical tools that Galileo had introduced, Newton turned a collection of observations into a single, powerful law. That law still guides the rockets that launch satellites today. The next step after Newton was taken by Albert Einstein. Einstein admired the way Galileo had trusted what the eyes could see, even when that sight went against common belief. Einstein's theory of relativity reshaped the idea of space and time, but it still rested on the same principle: observe, measure, then write a math formula. In a letter to a colleague, Einstein said, "The greatest scientists are those who have the courage to trust the evidence of their own senses." That echo of Galileo's method can be heard in every modern experiment that looks for tiny particles or distant galaxies. Even today, space missions depend on the same chain of ideas that began with Galileo's telescope. When a modern astronaut named a new space telescope after Galileo, the gesture was more than a tribute. The astronaut, Dr. Maya Patel, explained that the telescope would act like new set of eyes for humanity, just as Galileo's eyes opened a new window on the heavens. The telescope, now called the Galileo Orbital Observatory, will map distant exoplanets, measure their atmospheres, and test theories that trace back to Galileo's first sketches of planetary motion. One everyday analogy can help picture this chain of influence. Imagine building a house. The foundation must be strong, or the whole house will crumble. Galileo's work is that foundation. He laid down the idea that careful measurement and clear math can support any structure of knowledge. Newton added the walls, Einstein added the roof, and modern engineers add the wiring and plumbing that let the house function. Without that solid base, the later work would have been shaky at best. A second analogy uses a map. When a traveler wants to reach a new city, they first look at a map that shows the roads, the distances, and the landmarks. Galileo's observations and equations are like that map. They give later scientists a clear picture of how the world works, so they can plan their own journeys without getting lost. Newton followed the road that Galileo drew. Einstein took a shortcut that the map hinted at. And today's engineers follow the same routes to send probes to Mars and beyond. Not everyone agrees that Galileo's impact is as large as it is often described. Some scholars argue that the scientific method was already forming before Galileo, pointing to the work of earlier thinkers like Ibn al-Haytham, who studied optics, and to the medieval scholars who used experiments in alchemy. They claim that Galileo was simply the most famous messenger, not the origin of the method itself. Others say that the invention of the telescope, a piece of technology made by Dutch lens makers, was the real turning point, and that Galileo's interpretation was just one of many possible readings. These counterarguments suggest that the credit given to Galileo may be a bit overstated. Even with those doubts, the evidence shows that Galileo's specific combination of observation, experiment, and mathematics created a pattern that others could copy. When Newton wrote his Principia, he cited Galileo's experiments with falling bodies as the proof that acceleration is constant. When Hawking later spoke about black holes, he referred to the same idea that a simple law can describe a complex system, a notion that began with Galileo's study of motion. Stephen Hawking once said, "We are all made of star stuff, and the same laws that govern the stars also govern the smallest particles." That line of thought can be traced back to Galileo's claim that the same rules apply both on Earth and in the heavens. The influence of Galileo also appears in everyday technology. The simple pendulum clock, which keeps time by swinging back and forth, works because of the same principle that Galileo discovered. The period of a swing depends only on its length, not on its weight. This principle helped engineers design accurate clocks for navigation, which later made long sea voyages possible. Those voyages, in turn, opened new trade routes and spread scientific ideas across continents. Another real-world example is the use of lenses in eyeglasses and microscopes. Galileo's work with lenses showed how changing the shape of glass could bring distant objects into focus. That insight led to the development of microscopes that let scientists see cells, bacteria, and even viruses. The ability to see the very small has saved countless lives through medical advances, all because Galileo first proved that a simple tool could extend human sight. The story of the apple also carries a small twist that ties back to Galileo's own experiments. Galileo dropped balls of different masses from the Leaning Tower of Pisa to show that they fall at the same speed. Newton's apple fell from a tree, but the idea that objects of different weight fall together was already demonstrated by Galileo. The apple story, therefore, is not just about Newton's insight. It is a reminder that Newton built directly on Galileo's earlier proof. The modern telescope named after Galileo also shows how the legacy lives on in space exploration. When the telescope was launched, the mission control team quoted Galileo's own words: "You measure what is measurable, and make measurable what is not." They used that phrase as a motto for the team, reminding them that each new measurement pushes the boundary of what humanity can understand. The telescope will look at distant galaxies, test the predictions of Einstein's relativity, and perhaps even find clues about dark matter, a mystery that Galileo could never have imagined, but that fits the pattern he started. In the earlier part of this series, the importance of using mathematics to describe motion was highlighted. Galileo wrote, "Mathematics is the alphabet with which God has written the universe." By turning motion into numbers, he gave later scientists a tool that could be shared across cultures and centuries. That tool allowed Newton to write his famous equation, F-ma, which still appears in high school textbooks today. It also allowed engineers to calculate the thrust needed for a rocket to escape Earth's gravity, a calculation that depends on the same principles of acceleration that Galileo first measured. Einstein's work on the bending of light by gravity also reflects Galileo's early experiments with lenses. Galileo showed that a lens could bend light to bring distant objects into view. Einstein took that idea further, showing that massive objects bend the fabric of space itself, causing light to follow a curved path. The 1919 eclipse experiment, which confirmed Einstein's prediction, used a telescope similar in design to the one Galileo first built. The chain from Galileo's simple lens to Einstein's relativistic calculations shows how each step rests on the previous one. Even the language used by scientists today carries Galileo's influence. Phrases such as "the heavens are not immutable" echo his famous claim that the stars move and change. When modern astronomers talk about celestial mechanics, they are using a term that grew out of Galileo's study of planetary motion. The word mechanics itself was popularized by Galileo's description of how machines work, a description that Newton later expanded into a full theory. The counterargument that Galileo's impact is overstated often points to the fact that many of his ideas were already present in the work of ancient Greek thinkers like Aristarchus, who suggested that the Earth moves around the Sun. However, Aristarchus lacked the experimental proof that Galileo provided. Galileo's use of the telescope gave him direct evidence, and his careful recordings turned speculation into fact. Without that evidence, the idea of a moving Earth might have remained a philosophical notion rather than a scientific one. Another critique says that the scientific revolution would have happened anyway, because the Renaissance was a time of great change. While it is true that many ideas were in the air, Galileo's role was to tie those ideas together with a method that could be repeated and tested. The reproducibility of his experiments, such as the rolling ball down an inclined plane, gave later scientists a template for how to verify a claim. That template is still taught in schools as the basis of the scientific method. The influence of Galileo can also be seen in the way modern scientists communicate. In the early sections on observation, the importance of clear, detailed notes was emphasized. Galileo kept extensive journals, describing each experiment with sketches and numbers. Those journals were later studied by Newton, who copied the style in his own notes. Today, research papers follow the same pattern: describe the setup, List the data, explain the analysis. This format traces its roots back to Galileo's habit of writing everything down. A modern anecdote illustrates this lasting habit. Dr. Luis Ortega, a physicist working on quantum optics, once said that he reads Galileo's notebooks before starting a new experiment. He finds comfort in the fact that Galileo wrote down every step, even the failures. Ortega believes that this openness about mistakes is what makes science progress, a lesson that Galileo taught by publishing his own doubts about the motion of projectiles. The naming of the Galileo Orbital Observatory also sparked a moment of reflection among the mission's engineers. One of the chief engineers, Maria Chen, recalled a story from her childhood about a boy who built a small telescope from a magnifying glass and a cardboard tube. She said, "When I heard that the new telescope would bear Galileo's name, I felt a connection to that boy's curiosity. It reminded me that big discoveries often start with simple tools and a desire to see more clearly." That story ties the modern mission back to the simple act of looking up, which Galileo turned into a disciplined practice. In the realm of education, Galileo's legacy is evident in the way physics is taught. The classic problem of a ball rolling down a slope, first measured by Galileo, is still the first example in many textbooks. Students learn that the distance traveled is proportional to the square of the time, a relationship Galileo discovered by counting beats of a pendulum. Galileo Galilei lived at a time when the world was changing fast. He believed that human reason could uncover the secrets of the heavens. He also trusted the evidence that experiments gave. In the same way, a child who receives a new toy will try it out, push its buttons, and watch how it works. The child does not accept the maker's claim that the toy is perfect without testing it. The child uses reason and evidence, just as Galileo used a telescope and a falling stone experiment. This simple act shows how a mind can move from belief to knowledge. A citizen who goes to a poll to vote on a new law also follows the same pattern. The citizen reads the proposal, hears arguments, and looks at data about what will happen if the law passes. The citizen does not simply obey the ruler because the ruler says so. The citizen asks questions, weighs facts, and decides. This act of voting mirrors Galileo's call for freedom of thought. It shows that the same tools of reason and evidence that helped a scientist study the stars can help a society choose its path. Galileo's ideas did not appear in a vacuum. The Renaissance had already begun to value the ancient Greeks. Thinkers such as Plato and Aristotle had taught that the world could be understood by the mind. But Aristotle also taught that the heavens were perfect and unchanging. Galileo's observations of the moons of Jupiter and the phases of Venus contradicted that old view. He showed that the heavens could change, just like the earth. René Descartes, a French philosopher who lived a few decades after Galileo, took the trust in reason even farther. Descartes wrote, "I think, therefore I am." He meant that the one thing a person can be sure of is the fact that they are thinking. This simple statement puts reason at the center of knowledge. Descartes admired Galileo's method. He said that clear and distinct ideas, like those found in a good experiment, are the foundation of true knowledge. In this way, Descartes built on Galileo's trust in evidence. John Locke, an English thinker, also felt the pull of Galileo's example. Locke argued that the mind at birth is a blank slate, a tabula rasa. He wrote that people gain knowledge through experience and observation. This view matches Galileo's practice of learning from what the senses report, not from what tradition says. Locke also wrote, "All men are equal," which links the right to think freely with the right to be treated the same. Both Descartes and Locke saw Galileo's method as a model for how people should learn about the world and about each other. The core of Galileo's philosophy can be summed up in three ideas: reason, evidence, and the right to question authority. Reason is the tool that lets a person think clearly. Evidence is the proof that comes from experiments or observations. The right to question authority means that no one, not even a powerful church, can stop a person from asking why. These ideas appear throughout Galileo's famous dialogue, a book written as a conversation among three characters. One character, Salviati, argues for reason and evidence. Another, Simplicio, defends the old teachings of the church. The dialogue ends without a clear winner, but it shows how reason can clash with tradition. The conflict with the church began when Galileo pointed his telescope at the night sky and wrote, "And yet it moves." This short phrase, often quoted as "Oppure si move," means that the earth moves around the sun even if the church says it does not. The phrase captures the spirit of defying an authority that refuses to accept evidence. The church, which held great power, saw this as a threat. It feared that if people could question one teaching, they might question many others. This fear led to Galileo's trial and house arrest. One counterargument to Galileo's stance is that tradition protects social order. Some thinkers argued that long-standing beliefs keep societies stable. They said that if everyone started to question every rule, chaos would follow. In this view, the church teachings acted like a set of traffic lights. They guided people safely through the road of life. Changing those lights without careful planning could cause accidents. This argument holds that preserving tradition is a way to keep peace. A second counter-argument claims that authority holds wisdom that ordinary people lack. The idea is that scholars, priests, and rulers have spent years studying the world. Their conclusions are therefore more reliable than the guesses of a layperson. If a farmer or a child started to reject those teachings, the argument says the whole community could lose its shared knowledge. This view sees the church as a guardian of truth, not a barrier to it. It suggests that the right to question should be limited to protect the common good. Both counter-arguments have a grain of truth. Tradition does give people a sense of identity and continuity. Authority can indeed hold valuable knowledge. Yet Galileo's life shows why those ideas can also become obstacles. When the church refused to look at the telescope's pictures, it missed an opportunity to expand its own understanding. When Simplicio clung to old ideas, he stopped learning. The story reminds listeners that reason and evidence can improve, not destroy, the social fabric. Real-world applications of Galileo's philosophy appear every day. In schools, teachers use his experiments to teach the scientific method. A teacher in a small town once set up a ramp and a ball, just as Galileo did, to show how objects fall. The students watched the ball roll down, measured the time, and compared it to the teacher's prediction. The teacher explained that the experiment was a way to test a claim, not to accept it blindly. The class learned that knowledge grows from trying, measuring, and correcting. In another setting, a public art piece in a bustling city shows a giant bronze telescope pointing toward the sky. The sculpture stands near a courthouse, where judges hear cases about freedom of speech. The artist said the piece honors Galileo's courage to look beyond the accepted view. Passers-by stop, read a plaque that quotes Galileo. The book of nature is written in the language of mathematics, and think about how evidence can guide law as well as science. The art piece turns a public space into a reminder that reason belongs to everyone. Modern interpretations of Galileo's ideas can be found in the digital age. When a new app claims to predict health outcomes, users test it with their own data. They compare the app's predictions to real results, just as Galileo compared his telescope's pictures to the accepted model of the heavens. If the app fails, users question the claim and look for better evidence. This process follows the same pattern that Galileo set centuries ago: observe, test, revise. Another modern example comes from climate science. Scientists gather temperature records, ice core samples, and satellite data. They use reason to build models that explain the patterns they see. When politicians ignore the evidence, the public can point to the data and demand action. The climate debate shows how the right to question authority, when backed by solid evidence, can push societies toward better choices. It also shows how some still argue that tradition, such as reliance on fossil fuels, keeps economies stable. The tension mirrors the old clash between Galileo and the Church. Galileo also wrote about the freedom to think. He said, "Why do not feel obliged to believe that the same God who has endowed us with reason has intended that we should forgo it?" In plain words, he meant that being given a mind is a gift, not a prison. He believed that each person should use that gift to explore. This quote appears in many modern discussions about academic freedom. Students and professors alike invoke it when they face pressure to silence controversial ideas. The quote reminds them that the right to think is as important as any law. Descartes, who admired Galileo, also wrote, "If you would be a real seeker after truth, it is necessary that at least once in your life you doubt, as far as possible, all things." This statement tells readers that doubt is a tool, not a flaw. It fits with Galileo's method of questioning the Church's claims. Both thinkers show that doubt, when paired with evidence, leads to progress. Locke added, "All men have a natural right to liberty of conscience." He meant that each person can hold their own beliefs, as long as they do not harm others. This idea supports Galileo's fight for the freedom to publish his findings. It also underpins modern ideas about free speech. When a citizen votes, when a scientist publishes, when a teacher shows an experiment, they all act on the right that Locke described. The two relatable scenarios help bring these ideas home. The child testing a new toy learns by trying, failing, and trying again. The child does not accept the toy's manual as the final word. The child uses reason, looks at evidence, and decides if the toy works. The citizen voting on a new law reads the proposal, looks at data, and decides whether it helps the community. Both act on the same principle. They are not forced to accept an authority's word without question. They both rely on evidence and reason to guide their choices. The teacher's anecdote shows how Galileo's method lives on. In a classroom, the teacher set up a pendulum, just as Galileo did when he studied the swing of a lamp in a cathedral. The students measured how long each swing took and noted that the time stayed the same even when the swing was higher. The teacher explained that this regularity is a clue about how nature works. The students felt the excitement of discovering a rule themselves. The story shows that the practice of testing and observing is still a powerful way to learn. The public art piece anecdote adds a visual reminder. In a city square, a bronze telescope points toward a mural of the night sky. The plaque beneath it reads, "E per si move." Tourists stop, read the quote, and think about the courage to speak the truth. The sculpture stands near a courthouse, linking the fight for scientific truth with the fight for legal truth. The piece shows how Galileo's legacy reaches beyond science into law, art, and everyday life. When the Church condemned Galileo, it tried to stop the spread of his ideas. The Dialogue, his famous book, presented the debate in a way that let readers hear both sides. The character Salviati used reason and evidence, while Simplicio clung to tradition. The book ends without a clear verdict, but it forces readers to choose which voice they trust. This literary technique mirrors the modern citizen's choice at the ballot box. It also mirrors the child's choice to keep testing a toy after a failure. The story invites the audience to weigh evidence themselves. The conflict with the Church also shows why freedom of thought matters. When an institution says that a claim must be accepted without proof, it blocks the path to new knowledge. Galileo's experience teaches that a society that punishes questioning loses the chance to grow. The Church's fear of losing control led to a harsh response, but the ideas Galileo planted continued to spread. Over time, the same reason and evidence that the Church tried to suppress became the basis of modern science. The counterarguments about tradition protecting order still appear today. Some people argue that changing a long-standing law could cause unrest. They compare it to a building that has stood for centuries. Pulling down a wall might cause the whole structure to collapse. This analogy helps explain why some resist change. Yet, the building can also be improved by adding new rooms, stronger beams, and better windows. The same logic applies to ideas. Tradition can be a solid foundation, but it can also be a barrier if it stops improvement. Another counterargument says that experts know best. It likens society to a ship with a seasoned captain. The captain decides the course, and the crew follows. If every sailor tried to steer, the ship might go nowhere. This view values experience and hierarchy. However, the captain can also be wrong. If the captain refuses to look at new maps, the ship may sail into danger. Galileo's story shows that even experts can miss the truth if they ignore evidence. The lesson is that expertise should be open to testing. Modern philosophers still discuss these themes. Some argue that reason. Galileo's story does not end in a dusty museum. It lives on in the small choices that shape each day. In the earlier parts of this series, the viewer learned how Galileo broke with the old view of the heavens, how he used a telescope to see moons that never before had been named, and how he argued that the Earth moves because the evidence says so. Those ideas are now being tied to the way people think about truth in a world full of fast news and new gadgets. The final part asks the audience to bring Galileo's spirit into everyday life, to ask, to test, and to stay humble about what the senses can tell. The roots of Galileo's method go back to the ancient Greeks, but the real spark came in the early 17th century. Galileo Galilei, a mathematician from Pisa, grew up in a time when scholars still trusted ancient authority more than fresh data. He read the works of Aristotle, who said that heavy things fall faster than light ones, and he also read the writings of the new thinkers who wanted to base knowledge on observation. One of those new thinkers was Francis Bacon, who wrote that knowledge should be built on careful experiments. Bacon's call to make experiments helped Galileo feel free to point a telescope at the night sky and write down what he saw, even when the Church disagreed. Galileo's most famous argument is simple. Look, measure, repeat. He pointed his telescope at Jupiter and counted 4 bright spots moving around the planet. He wrote, "Measure what is measurable, and make measurable what is not." By counting the moons, he showed that not everything circles the Earth. He also rolled balls down inclined planes and timed them, showing that the speed of a falling object grows in a steady way, not in jumps. These experiments gave him a way to talk about the world that did not need a priest to approve it. Other thinkers built on Galileo's work. René Descartes, a French philosopher, liked the idea that the world could be described with mathematics, a view that Galileo had already used. Later, Isaac Newton took Galileo's experiments with falling bodies and added the idea of universal gravitation, turning a set of observations into a law that works everywhere. In modern times, scientists such as Carl Sagan and Neil deGrasse Tyson have spoken about the need to keep asking questions, just as Galileo did. Their words remind us that the habit of testing ideas never grows old. The core of Galileo's spirit can be summed up in 3 steps. First, notice something that seems odd or interesting. Second, find a way to test it with simple tools. Third, share the result and let others try it too. This pattern fits many modern tasks. When a person sees a headline that sounds shocking, the first step is to notice the claim. The second step is to check the source. compare the story with other reports, or look for data that backs it up. The third step is to decide whether to share the story, and if they do, to note that they have checked the facts. In the same way, a cook who wants to try a new recipe first tastes the sauce, adjusts the seasoning, and then serves it only after confirming the flavor is right. Both actions echo Galileo's call to test before trusting. The first everyday example is checking facts before sharing a news article. Imagine a friend sends a link that says, "Scientists have found a cure for the common cold." The first reaction might be excitement, but Galileo would ask, what proof is there? The person can look for the original study, see if reputable journals have published it, and compare the claim with other experts' opinions. If the evidence is solid, the story can be shared, perhaps with a note about the source. If not, the story stays private. This simple habit keeps rumors from spreading, just as Galileo's experiments kept false ideas from spreading in his time. The second everyday example is testing a new recipe before serving guests. A home cook reads about a new dessert that uses a different type of flour. Instead of making a full batch for the party, the cook tries a small spoonful, notes the texture, and adjusts the amount of sugar if needed. Only after the test is successful does the cook prepare the full dish. This mirrors Galileo's method of using a small experiment before making a big claim about the heavens. Even with such clear steps, there are warnings about overconfidence in personal observation. One counterargument says that the senses can be fooled. Optical illusions show that the eye can see two lines as different lengths when they are the same. Galileo himself noted that a telescope can make stars appear as points of light, but the instrument also adds its own distortions. If a person trusts only what they see without checking tools or methods, they may draw the wrong conclusion. This caution reminds modern readers that a single observation is not enough. It must be repeated and compared. A second counterargument focuses on the need for theory to guide observation. In Galileo's time, some scholars argued that looking at the sky without a proper mathematical framework would lead to random guesses. They said that a good theory helps decide what to look for and how to measure it. Today, a person who reads a headline might feel that checking one fact is enough, but without understanding how the information fits into a larger picture, the person could miss hidden bias or deeper errors. The lesson is that observation and theory must work together, just as Galileo used mathematics to make sense of his measurements. Modern science communication offers many examples of how Galileo's spirit is kept alive. The popular podcast Science takes a claim, such as "Does coffee improve memory?" and tests it by looking at studies, interviewing experts, and summarizing the result. The host does not claim to be the final authority, but instead invites listeners to see the process. Another example is the YouTube channel Veritasium, where the presenter builds simple experiments, like dropping objects from a height, to show how physics works. Both channels model the three-step pattern of noticing, testing, and sharing. Analogies help bring the abstract ideas down to daily life. Think of a detective solving a mystery. The detective first hears a rumor, then gathers clues, then checks those clues against the evidence, and finally tells the story. Galileo acted like a detective of the sky. Another analogy is a gardener tending a garden. The gardener watches how a plant grows, tries different amounts of water, and notes the result before deciding how to care for the whole garden. In both cases, the careful testing before a big decision reflects Galileo's method. History offers more stories that show the power of this approach. In 1999, a high school student named Maya built a small pendulum to test whether the length of a swing changed the speed of a swinging ball. She read about Galileo's experiments with inclined planes and decided to use a modern stopwatch and a ruler. Her data matched Galileo's predictions, and she won the state science fair. Maya's project shows how a teen can follow the same path Galileo took. Ask a question, design a simple test, and let the numbers speak. A second anecdote comes from a small town that wanted to redesign its central park. Some residents suggested a large fountain, while others wanted a playground. A local council member remembered Galileo's call to test ideas. She organized a community workshop where participants built small models of both designs using cardboard and measured how much space each used, how many people could walk through, and how much noise each generated. The test showed that the playground allowed more movement and less echo, so the council chose that option. The story shows that even a town can use a mini-experiment to decide between big plans, echoing Galileo's method of letting evidence guide choices. Modern thinkers also warn against using observation without humility. The philosopher Thomas Kuhn wrote that scientists work inside paradigms or accepted ways of seeing the world, and that they can miss new ideas when they cling too tightly to old views. This idea supports the caution that overconfidence in one's own senses can block progress. Similarly, the statistician Nate Silver stresses the importance of probabilistic thinking. He says that even strong evidence can be wrong, so it is wise to keep a margin of doubt. Both points echo the ancient warning that the observer must stay aware of limits. Putting all the pieces together, the video can now link back to the earlier sections. The first part explained how Galileo challenged the geocentric model that placed Earth at the center of the universe. The second part showed how he used mathematics to describe motion, turning shaky ideas into solid laws. The third part explored how his conflict with the Church taught a lesson about the power of ideas versus authority. The current segment adds a practical layer, how the same habit of testing can help a person decide whether to share a story or serve a new dish. The thread that ties everything together is the idea that truth grows when people look, measure, and repeat, rather than when they accept the first claim they hear. In daily life, the habit of checking facts before sharing a news article can stop the spread of false rumors. It can also protect a person's reputation because sharing something untrue can hurt trust. The habit of testing a recipe before serving guests can avoid embarrassment at the dinner table. It also encourages creativity, because a small test can reveal a better flavor that the cook can then share with more people. Both habits show that the simple act of testing makes life smoother. The two counterarguments remind the audience not to become too proud of a single test. The first warns that the senses can be tricked, so tools and repeated checks are needed. The second reminds that a theory or broader context helps interpret the data. Together they suggest a balanced approach. Test, but also compare, discuss, and stay open to correction. The two anecdotes bring the ideas home. Maya's high school science fair project shows that a teen can follow Galileo's path with a stopwatch and a ruler, turning a curiosity about motion into a winning experiment. The park redesign story shows that a whole community can use a small model to decide between big ideas, keeping the decision rooted in evidence. Both stories prove that the method works at any scale. The modern voices of Carl Sagan, Neil deGrasse Tyson, and the hosts of For Science for Cess and Veritasium remind viewers that the world still needs people who ask, what can be measured, and who share the answer in a clear way. Their work keeps Galileo's spirit alive in the age of the Internet, where information spreads faster than ever. To finish, the narrator can offer a gentle challenge. When a new app appears on a phone, the viewer can try it for a few days, note what works, and decide whether it truly helps. When a rumor starts at work, the viewer can pause, look for evidence, and then speak only after the check is done. In each case, the viewer follows the same three-step rhythm that Galileo used centuries ago. The final thought is that the world does not need a hero who never doubts. It needs a habit of careful watching, simple testing, and honest sharing. Galileo showed that even a single person with a telescope and a notebook can change how humanity sees the sky. Today, a person with a phone and a curious mind can change how the community sees a story or a meal. The lesson is timeless. Keep the eyes open, keep the tools ready, and keep the mind ready to learn from what the test shows. By weaving together the origins of Galileo's method, the key thinkers who expanded it, the arguments that support it, the cautions that keep it honest, the everyday examples that make it real, the modern voices that keep it fresh, the analogies that simplify it, the historical anecdotes that inspire it, and the quotes that give it weight, this segment completes the journey. The viewer now has a clear map from the night sky of the 17th century to the news feed of the 21st, and a gentle reminder that each small test is a step toward a clearer view of the world.